everyone, my name is Ludmila Glinskih. I would like to present you our joint work with Artur Riazanov. In this work, we show that partial minimum branching program size problem is ETH-hard. So before I define minimum branching program size problem, let me define minimum circuit size problem, which motivated our work. As an input, minimum circuit size problem, also abbreviated usually to MCSP, receives a truth table of a Boolean function and the size parameter S. And it outputs yes if this Boolean function f can be computed by a circuit of size at most S and no otherwise. And we usually consider De Morgan circuits with fan-in too. So why it is important to study MCSP and what we know about it? We know that MCSP is in NP, and to see that you can just guess a circuit and check whether this circuit computes function f or not. And since the input of the function is a whole truth table of the Boolean function, we can easily do that in NP. We also know that if MCSP is in P, then there are no strong PRGs. And if we would be able to show that MCSP is NP complete, then we would get that exp is not equal to ZPP. Important to note here that we actually believe that exp is not equal to ZPP. Exp is a huge class, ZPP is not so much, but it's was surprisingly hard to show. So you can see that understanding MCSP better would actually help us to resolve some open problems in structural complexity. And interestingly enough, if we would understand complexity of MCSP in restricted classes of computations, we would also get like really cool consequences. For instance, if we could show that MCSP cannot be computed by a branching program of size n to the 2.01, or like even any constant in the exponent that is a bit bigger than 2, or similarly a lower bound for circuits of size better than like linear, then we would get that the whole class of NP is not contained in the n to the k circuit slice for branching program circuits. So yeah, it would be really nice to understand MCSP better. That's why we studied, like it's that popular to study it in the recent years. So to understand MCSP better, we can also study not MCSP itself, but different variations of MCSP. Specifically variations of MCSP for weaker circuit classes. For instance, we can study minimum C circuit size problem, in which the input is exactly the same, truth table of a Boolean function and size parameter. And now we output yes if n can be computed by a circuit of class C of size at most S. For these circuits from different classes of circuits can be either DNFs or DNFs of XORs and AC0 formulas, from which we already know that it's NP-hard to compute MCSP for them. And we also know that it's ETH-hard to minimize the Morgan Boolean formulas. And in this work, we study complexity of minimizing branching programs or minimum branching program size problem. All right. Before I describe you our results, I would like to just remind you the definition of branching programs. So branching programs is a way to represent the Boolean function. We represent the Boolean function by a directed acyclic graph with exactly one source and two sinks. One sink is labeled with 0, and now the sink is labeled with 1. All other nodes are labeled by a variable, and all the edges are labeled by either 0 or 1 values. To compute a value of the function on the input, for instance, if we have the substitution like that, a equals to 0, b equals to 1, c equals to 1, We start at the source of the branching program, look at its label, it's labeled by A, look at the value of A into the substitution. It equals to 0, we use 0h. We get to a new node, it's labeled by variable B, we look at the value of B in substitution, it's 1, we use 1h, and we get to a sink, and the label of the sink is exactly a value of this function on this substitution. The multiple complexity measures corresponding to branching programs. In this work, we focus on the size of a branching program, which is basically the number of all vertices which are labeled by a variable. We also have a few results corresponding to restricted versions of branching programs, and we focus on with K restriction. We say that the branching program, with K branching program is with K branching program if on every path from the source to the sink, every variable occurs no more than K times. And we also focus, we'll mention, oblivious read-once branching programs, and they also known as OBDDs. This is the same branching program as read-once branching program, but we also have additional restriction of order. So on every path from the source to the sink, all variables appear in exactly the same order. From the structure complexity point of view, branching program is a very important mode of computation because it captures space complexity of the computation. And for instance, the class of languages recognized by non-uniform family of branching programs of polynomial size is exactly a class of languages that can be recognized by Turing machine with logarithmic amount of memory, which use non-uniform advice of polynomial size. And the connection of the size of branching programs with the space complexity gives us a really nice instrument, nice way to prove lower bounds on the space complexity of, for example, streaming algorithms through proving lower bounds on branching programs. Complexity of branching program minimization was already studied extensively before work. For instance, quite a few results were known for minimization of OBDDs and read-once branching programs. So it was already shown to be ETH-hard to compress an input OBDD and to compress input read-once branching program. Again, this setting is different from the setting of MCSP, since in MCSP as an input we receive a truth table, which is long, and if you're given an OBDD or read-once branching program as an input, it can be already quite succinct. So it is harder to compress something small because you have fewer steps you can do to actually check configurations. Similarly, it was shown to be hard to minimize, to find a matching OBDD of size S if we're given a set of pairs, a set of substitutions, input value of the function. And it was also shown to be hard to approximate the size of the minimum read-once branching program consistent with this same set of substitutions. On the bright side, if we are given a complete truth table of the total function, we have a polynomial time algorithm for checking whether there is an OBDD of size most S that computes this function. Note that since the length of the input of MCSP or minimum OBDD size problem is 2 to the little n, and we have the algorithm with a runtime 3 to the n, this is actually a polynomial time algorithm in the length of the input. So we can decide total version of OBDD minimization very efficiently. But if we have a succinct input, then it's becomes NP-hard to minimize OBDs and read-once branching programs. So now to the setting that we are working with. We are working with partial version of minimum branching program size problem. As an input, again, we receive a truth table of a partial Boolean function, which now has, for each input of the function, we have either value 0 or 1 or a star, which means undefined value, and a size parameter s. And we need to output yes if there exists a total function g, which is consistent with this input function f, and that can be computed by a branching program of size at most s, and no otherwise. So, difference with the previous results for partial functions is that even if we don't assign some bits, we don't substitute values, we still put a star and have really long input. So it makes it harder to show hardness of this problem because the input is long, we have more time to post-process this truth table to do something with it. This is the main intuition why this problem is not known to be NP-hard yet. Maybe it will not be NP-hard overall. Okay, so what we showed in our work. So we showed that assuming exponential time hypothesis, every Turing machine computing partial minimum branching program size problem requires time n, capital N, to the log capital N, where capital N is 2 to the little n, the length of the truth table. So this function is super polynomial. So we basically show that assuming ETH, this partial MBPSP cannot be solved in polynomial time. And important that our result also holds for minimizing not only general branching programs, but also restricted branching programs such as read-once branching program, read-k branching programs for every integer k, and OBDs. One of the motivations for studying a partial version of minimum branching program size problem is to develop techniques which will help us to construct reduction from partial MCSP to total MCSP. Let me explain why. So we know that minimizing the size of DNFs is NP-hard, and minimizing the size of De Morgan formulas is ETH-hard. But both of these results, though now they hold for total versions of this minimization problem, but they were first shown for partial minimization problems. And we already know that partial MCSP is ETH-hard and partial MCSP is NP-hard under randomized reductions. And in this work we show that partial MBPSP is ETH-hard. But since we understand branching programs a bit better than circuits, for example, the best lower bounds for branching programs is quadratic versus linear for circuits, we believe that if we could be able to construct a reduction from partial MBPSP to total MBPSP, then it will help us develop some new techniques for constructing reductions from partial MCSP to total MCSP. One extra intuition about that is that both branching programs and circuits have as an underlying structure graph, directed acyclic graph, not just a tree as DNFs and De Morgan formulas. So this structure adds more complexity to analyzing these models. But this is also some intuition why branching programs and circuits may be a bit similar, and some techniques from branching programs can help us to understand circuits better. But we'll see how it goes. So now get into the proof ideas for how we show hardness of branching program minimization problem. And by MBPSP star, we denote a partial version of minimum branching program size problem. So I restate the theorem here, and I wanted to note that we use the same proof structure that was introduced by Lange in the work when he showed that partial version of MCSP is ETH-hard. but we adapt it for branching programs. So we start with the following problem that is known to be ETH-hard. We show that this problem called bipartite permutation-dependent set problem. Shortly, it's a very complicated graph problem. I will explain its intuition on the next slide. And it was known to be n factorial hard under ETH. And we construct exponential time reduction to partial MBPSP. And since we start with a function that is n factorial hard and we construct a reduction that takes like 2 to the n time, we still have some hardness left to get super polynomial lower bound on MBPSP star. So now some intuition about this bipartite permutation-dependent set problem. Its definition is complicated, but I think it's very helpful to understand its definition, to understand the hardness reduction and why this problem is so helpful in the reduction. So in this is a graph problem, and it has this graph problem. Each instance has many vertices, and we can just put all these vertices on a grid of size 2n by 2n. And even though it has so many vertices, we actually can focus only on these 2 quadrants of vertices, because edges between in this graph exist only between vertices from these 2 quadrants. And now this input graph is a yes instance of the problem if we can choose exactly 1 vertex from each row and exactly 1 vertex from each column, such that this set of vertices form an independent set. So this is an example of what would be the solution of this problem, like the proof that this is a yes instance of this problem. So it looks complicated, but again, we chose exactly 1 vertex from each row and exactly 1 vertex from each column. By that, we define the permutation on the set of size 2n. And since we chose only vertices that are not connected by an edge, we chose an independent set. So this is both a permutation and an independent set. And just by definition, it's a bipartite graph because we connect by edges only vertices from different quadrants. So this is where the definition comes from. Okay, and this problem is n factorial hard because it's both NP-hard problem of finding an independent set, and also each independent set encodes a permutation. So essentially, if ETH holds, you need to find one of the permutations, and it's equally hard to find each permutation, so you have to check all permutations to find a solution. At least all permutations within 1 quadrant. Okay, so now back to our reduction. So we start with the instance of this problem. It's a graph, and based on this graph, we construct a partial truth table, which has 0, 1s, and stars. And if the small quadrants of the input graph were of size little n, then our partial function will depend on 6n variables. And the key lemma that there exists a total function consistent with gamma g, which can be computed efficiently by a branching program of size exactly 6n, if and only if g is a yes instance of BPIS, bipartite permutation dependent set problem. Note here that we prove that the branching program, this gamma g, should be computed by a branching program of size exactly 6n, and the function itself depends exactly on 6n bits. So basically we either can construct a branching program that queries every variable at most once or not. This is the main intuition. Yeah, I will not have time to explain much of this proof, but just a few ideas. So a reminder that gamma depends on 6 variables, and if G has a bipartite permutation dependent set, then we can efficiently compute gamma G by a very restricted version of branching program in which every variable occurs at most once. And this is just an example of a branching program in which every variable occurs once. So you can see, like, we have different nodes, different labels. We call such branching program a once appearance branching program. It's very restricted. So if a function depends on 5 variables, then this branching program will have size at most 5, which is a very huge restriction. And since we know that gamma is sensitive in all variables, we know that its size of branching program computing it should be at least 6n. So if we know that we can find the branching program of size at most 6n computes it, and we know that every branching program requires to read at least once each variable, we get that the size is exactly 6n. So we know that if there is a nice bipartite permutation dependent set, then we can construct a very small branching program that queries every variable exactly once. But surprisingly, even in the opposite direction, similar thing works. If we have a very small branching program, once appearance branching program, that queries every variable exactly once, and that computes this function gamma, then we can extract a permutation on the set of size to n, which will correspond to an independent set in original graph G. So again, I will not have time to cover that in more detail, but just like some intuition how exactly we extract this permutation from a branching program. So just by definition, this function gamma G depends on 6n variables, and we can split the 6n variables into 3 groups: x variables, y variables, and z variables. And every once appearance branching program that computes this function gamma has a very specific shape. Just illustration of how it should roughly look like. So this, if we would topologically sort the nodes of this branching program, then the path from the source to the sink will go through the triplets of variables xyz, xyz, xzy. They will be like some permutations of variables x, y, and z, but they will be grouped by types. So they will be first 3 variables will have exactly one x, exactly one y, and exactly one z. The next triplet will also have exactly one x, exactly one z, and exactly one y, and so on. Moreover, in each of these triplets, variables y and z will have exactly the same label, exactly the same index. And if for every such triplet we would map indexes of x to indices of y, we would actually get a bipartite permutation in the original graph G. Sadly, I don't have much time to go into more detail of the proofs and the ideas, but just a quick overview of the corollaries we get and the future work, that future directions that we see interesting. So since we show ETH hardness of general branching programs through this corner case, in which we either can compress branching program, truth table, to a branching program of linear size, where we query each variable exactly once or not. We actually get that, assuming ETH, for every k, compressing a truth table to read k branching programs or read once branching program requires the same runtime. It cannot be sped up by much. So, and similarly results, this result holds also for OBDDs, because once appearance branching programs are also OBDDs. Another corollary that we got is an unconditional rebound on the size of read once non-deterministic branching program computing MBPSP. Note here that there's an unconditional result, and it's not for partial version of minimum branching program size problem, but for total version of branching program size problem. And to prove that, we use ideas developed with Artur, Riazanov in our previous work, and essentially we use a similar framework as we had now. We start with bipartite dependent set problem, and we look at its reduction to MBPSP star. From our previous work already, we showed that BPIS is unconditionally hard for once optimistic branching program, and that reduction that was originally introduced by Rahul Langa was also computable by a once branching program. And actually, MBPSP star and MBPSP, partial version and total version, have exactly the same complexity in non-deterministic branching program model, because instead of stars in the definition of a partial truth table, we can just add non-deterministic guessing nodes. This is just some quick intuition on why it is so. But the main idea is that if we would have a small branching program computing MBPSP, we'd have a small non-deterministic branching program computing MBPSP star, and then we would have a small branching program computing bipartite independent permutation set problem, and we know that unconditionally it's not true. So through this framework, we would get an unconditional lower bound for MBPSP. One of the main next steps is to show hardness of MBPSP, similarly to what was already shown for De Morgan formulas and DNFs. One of the ideas we had is to use ideas similar to what Ilanga used to show reduction from partial formal minimization to total formal minimization. But we're not sure about that, because branching programs are very good in reusing some of the computations, because they can rewire, and it makes it hard to analyze, similarly to circuits. But we think that it's feasible to show reduction from partial read once branching program minimization, read k branching program minimization, to total read once read k branching program minimization. So we also would like to understand better are there any connections of hardness of MBPSP to other areas, to other structural complexity results. For example, MBPSP similarly to MCSP is a sparse language. So, and there are already results focusing specifically on sparse languages. But are there any results specific to minimization of branch programs? Maybe some connections with streaming algorithms or something else? It would be cool to know. And we also would like to understand the once appearance branch programs, or BPs, better. This is a very, very restricted computational model. So, like, branching program can query every variable at most once, which is a bit crazy and weird. But we already know that they are a bit more powerful than read once De Morgan formulas. But maybe there are any other connections maybe they are similar with some other restricted computational model. It will be nice to know. Okay, so quick recap. So we showed that partial MBPSP is ETH-hard, and we also showed that this result holds for various restricted versions of branching programs. We showed a conditional lower bound for the size of read ones, non-optimistic branch program computing, branch program minimization for various restricted and general branch programs. And we also showed NP and co-NP hardness of compressing branch programs. Okay, that's all. Thank you so much for your attention.